Hi everybody, today we are starting a class on group theory. We start with the basic definition of the group theory. Suppose we have a set of elements. For example, we consider a set I. I actually denotes the set of all integers. Okay. So here I is the set of all integers that is shown here. And the set of integers in this set have four properties. First property is sum of any two elements of the set I is again an integer, okay, and hence belongs to the set I. So if you take any two elements from this set and add them, you will get an element in the same set, because I is a set of all integers, all possible integers. Okay, and the second thing is the set contains an element 0. There is an element 0 in it, which is called the identity element, which has the property that for any element, if you take any element from the set, okay, if you take any element from the set, if you take any element from the set, we have sum of which has the property that for any element m plus 0 plus 0 plus m, that is equal to m. Okay, so m is any element from this set, and if you add the 0 with it, you can see that is equal to m. Now for every element m of the set I, there exists a unique element. Okay, for every element, the property C, for every element m of I, there exists a unique element n, which also belong to the set I, such that m plus n is equal to n plus m, that is equal to 0. Okay, you take any element, for example 2, then there is minus 2 in the set, so 2 plus minus 2, that is equal to 0. If you take another element, say 10, there is minus 10 in the set, so 10 plus minus 10, that is equal to 0. Okay, and clearly here we can see n is equal to minus m, so that is the third property. Then the fourth one is associative property. If m, comma n, p are any three elements of the set I, okay, the property D, if m, comma n and p are any three elements of the set I, m plus n plus p, that is equal to m plus n plus p. Okay, so we have the law of addition is associative. What we can say is this is associative. Okay, now consider, so this example of set of integer I, we see it has got four properties. Okay, now we look at another example. Now we are taking a set of all unitary matrices of order n. UN means set of all unitary matrices of order n. Okay, this set also has four properties. Okay, four properties. The first one, if U and V are any two unitary matrices of order n, then their product, now we are taking the operation product, the product UV, okay, UV is again a unitary matrix of order n and hence belongs to the set UN. So what is UN? UN is our set. That set contains all possible unitary matrices of order n. Okay, so if you take product of any two unitary matrices, you will be getting a unitary matrix, that we know. When you multiply two unitary matrices, we will get a unitary matrix. Okay. Now, so the first property A, the property B, the set contains the unitary matrix I. I is what? I is the identity matrix, which is a unitary matrix, which has the property UI, IU. Okay, that is equal to U. Okay, so U is any unitary matrix belonging to the set UN. So UI, IU, that is equal to U. Okay, so that is the property B. Now the property C, if U is an element of UN, okay, the set UN, there exists a unique element, a unique matrix V, which is also in UN, okay, such that UV, VU, that is equal to I. What is I? I is the unit matrix, which is a unitary matrix present in the set. So you take any matrix U, there is a unique element which is also unitary matrix. Okay, when you take the product UV, you will be getting VU, that equal to I. So third property over. The fourth one, if U, V and W are any three elements of the set, U, V, W are any three matrices, any three unitary matrices from the set, associative law for matrix multiplication. We know matrix multiplication is associative, whether it is unitary or not, it is associative. So U, V, W, that is equal to U, V, W. Okay, so we have taken two examples, one of the set of all integers, okay, then we have taken the set of unitary matrices UN, and we see these two sets, set of integers under the operation of addition, and the set of unitary matrices under the operation of matrix multiplication are very much similar in nature. Okay, the four properties satisfied by these two sets are very much similar in nature. In fact, these properties define a group. Actually, through these two examples, we have seen the definition of the group. And both sets, set of integers under addition, the set of unitary matrices under matrix multiplication, both are examples of a group. Okay, so now we are in a position to define a group. So what is a group? Group is, see the definition, group is a set of distinct elements. Distinct elements means it should not repeat, the elements should not repeat. Okay, where G equal to set of elements E, A, B, C, D, endowed with a law of composition. Okay, when you define a group, the set of elements should be having some law of composition, how the elements come together or go together. So maybe it is addition. In the case of set of integers, we saw it is addition. It may be multiplication. In the case of set of unitary matrices, we saw it is multiplication. Sorry, matrix multiplication, or it can be multiplication. Okay, so some law of composition will be there related with the set. Okay, and that is not enough. What? It should satisfy four properties. The first one, the composition of any two elements A and B of this group G. Okay, the composition. The composition of any two elements A and B of G under the given law results in an element which also belongs to G. Okay, thus A composition B belongs to G, B composition A belongs to G. See, for composition we are using a symbol circle, small circle, which denotes composition. So it can be, that law of composition can be addition, multiplication, matrix multiplication, etc. Okay. Now, the second property, there exists an identity element. Okay, there exists an identity element E belonging to G such that for all elements, for all A belonging to G, if you take the composition with the E composition A, that is equal to A composition E, that is equal to A. Okay. Now for any element A belonging to G, there exists a unique element, that is the third property, B, which is also belonging to the same set G, such that A composition B composition A, okay, A composition B composition A is equal to E. Okay, in this case the B is called the inverse of A. Okay, B is called inverse of A and vice versa. That means A is called inverse of B. Okay. Now we consider the fourth one. The fourth property, the law of composition of the group of elements is associative. Okay, the law of composition is associative for any A, B, C elements in the group, A composition, B composition, C, that is equal to A composition B, then composition C. So we have now seen the definition of a group. Group is a set of distinct elements. Okay, the elements should be different, there should not be any repetition. It is endowed with the law of composition. Okay, whenever we define a group, we will say the law of composition, addition or multiplication, matrix multiplication, etc. Okay, such that the following four properties are satisfied. The first one is the closure property, that is, if you take any two elements in the set in the group and when you take the product, okay, when the two combine, A composition B, that should give A composition B or B composition A, that should give an element in the same group. That is the first property. Then in every group there will be an identity element. How do you identify an identity element? If you take the composition of any element with the identity element, you will be getting the same element. Okay, that's how you identify the identity element. And for every element there exists a unique element such that A composition B composition A, that is equal to the identity element. Okay, in that case B is said to be the inverse of A or A is said to be the inverse of B. Then the fourth one, the associative law. If you take three elements, A composition B composition C, that is equal to A composition B composition C. Now I think you have understood the definition of the group. We have seen two examples of it. Actually we first saw the examples and then we came to the definition of the group. Order of the group. Order of group is the number of elements in a group. Okay, number of elements in a group is called its order. Okay, so if there are 5 elements in a group, we say its order is 5. Now finite group. What is a finite group? Finite group is a group containing finite number of elements. Okay, a group containing finite number of elements is called a finite group. Then what is infinite group? A group containing infinite number of elements is called an infinite group. Okay, that's quite simple. Finite group, finite number of elements. Infinite group, infinite number of elements. An infinite group may be further divided into discrete or continuous. Okay, an infinite group may further be discrete or continuous. Discrete means the number of elements in the group is denumerably infinite. Okay, this is countable, denumerably countable. Okay, for example, the first example that we saw, the set of all integers, that is actually an infinite group because there are infinite number of elements in the group. But it is discrete one. Okay, because you have 0, then 1, then 2, then 3, like that. So it is discrete. Then the continuous group. What is continuous group? If the number of elements in a group is non-denumerably infinite, that means if it is not countable, such as number of all real numbers. Okay, if you take a real number, there will be numbers in between 0 to 1. There will be very large number of numbers, infinite number of numbers. So it is continuous. Okay. Now, for the discussion that follows, we will not be using this circle symbol for composition. Okay, we will be simply A composition, B will be simply AB. If I write AB, that means A composition B. That does not mean we have to multiply A with B. It can be actually matrix multiplication or addition, it can be subtraction, it can be anything like that. Okay, so if I write AB, that means A composition B. Similarly, we shall replace the word composition. We will not be using composition henceforth. We will be using just multiplication or product. Product of two group elements. We will be simply saying product of two group elements. That does not mean the multiplication. Can be multiplication, it can be other operations as well. Okay, the product of the group elements is not necessarily commutative. Okay, the product of the group elements not necessarily commutative. In general, AB is not equal to BA. Okay, if it is commutative, AB will be equal to BA. Now we have the abelian group. Abelian group is a group where all elements of the group commute with each other. If all elements of a group commute with each other, it is said to be an abelian group. Okay, so it's an important class of group. Now, the groups, the set of integers that we saw, okay, the set of integers, the first example that we saw, that is actually an abelian group. Because if you take any two elements, for example, 1 and 2, 1 plus 2, you know, that is equal to 3. 2 plus 1, that is also equal to 3. That means all elements in the set of integers is commutative. Okay, so it's an abelian group. Okay, now all the groups, we will see certain groups now. But when it comes to the set of unitary matrices, so we saw the second example, set of unitary matrices of order n. That is not an abelian group. Why? Because matrix multiplication is not commutative. In general, it is not commutative. So it's not an abelian group. So if a group has to be an abelian group, all the elements of the group, okay, commute with each other. All the elements of the group commute with each other, then it is said to be an abelian group. Otherwise, it's a non-abelian group. You will see few examples of group. See 1 minus 1. This set, just two elements. This is actually a group. You know, if you take product of any two elements, we have only two elements, 1 and minus 1. If you take the product 1 into minus 1, you will get minus 1. Minus 1 into 1, minus 1. So you are getting the same, an element in the same group. So closure property is satisfied. Second example, then in this example, see this 1, this is acting as the identity element. Okay, this is acting as the identity element. 1 is identity element because if you multiply 1 with minus 1, you get the same element. Okay, minus 1 you are getting. 1 with 1, you get 1. Okay, so I1 is identity element. And what will be the inverse of minus 1? What is the definition of inverse? If you multiply an element with another element in the set, you should get identity element. So here when you multiply minus 1 with the minus 1, you will get 1. So what is inverse of minus 1? Minus 1 itself. Okay. So all the properties are satisfied. Its law of composition is multiplication. Next we take the second group. Second group consists of 4 elements, 1i minus I minus 1. Okay, 1i minus I minus 1. So this is a group under ordinary multiplication. We are defining the law of composition as multiplication. See, you should be now able to see the closure property satisfied. 1 into I, that is in the group. I into minus I. What is I into minus I? That is plus 1, that is in the group. Minus I into minus 1, I, that is in the group. So you take product of any two elements, you get the same element in the same group. So closure property satisfied. There is an identity element, that is 1. Okay. Then inverse. If you multiply I with minus I, you are getting 1. So that means inverse of I is minus I. Okay. What is the inverse of minus I? That is I. What is the inverse of minus 1? Minus 1 itself, because when you multiply minus 1 with minus 1, you are getting 1. So that is the inverse of minus 1. Then associative law is clearly satisfied. Okay. Now take these 4 matrices. This actually forms a group. If you multiply any two elements, okay, any two elements, you will be getting third element. Any element in the same set. Okay. And this E that forms the identity element. So operation is matrix multiplication. Okay, and 4 elements are there, and the identity element is this unitary matrix E. Okay, inverse B square is E. If you take B square, that is E. That means B is the inverse of B. And AC CA, that is equal to E. If you take AC into AC, that will be equal to CA, that is equal to this E1001 matrix, that is the unit matrix. So that means C is the inverse of A and A is the inverse of C. So this forms a group. Okay, so these are few examples of the group. So in this class, we have defined what is a group. Okay, we know it is a set of distinct elements having a law of composition, satisfying 4 properties. 4 properties are there, and that forms a group. And we have seen few examples of the group as well.